And number 19, determine whether it is continuous at 6. Continuity can only be tested at a specific point, and we're going to test to see if it's continuous at a 6. So our continuity test had 3 parts. So it's a 3-part test at a minimum. Number 1, prove or show that f at your point exists. So does f at 6 exist? So is it defined at 6? That's what we're talking about. Is it defined? Times that it won't be defined is if you're taking the square root of a negative or you divide by 0. So that's the first thing I'm going to do. I'm going to show that f at 6 exists. So it's only defined at 6 at the piece where it says 5 times x plus 10. So that means we have 5 times 6 plus 10, which is 30 plus 10, or we get 40. So f at 6 is definitely defined. Our output is 40. So we know that it exists and it's defined at 6. Okay, now the second test and the third test are pretty similar. I'll start here. I want to prove that the limit as x approaches 6 from both sides, I'm going to start from the positive side the first time, of our function f at x, which is a piecewise, approaches the same value of 40. Or I just want to figure out what the limit of this is. So what is the limit of f at x as x approaches the positive 6? So what I did is I had loaded those functions into the graphing calculator. So I'll show you that first. I put in the 2 pieces, x squared plus 4 and the 5x plus 6. Since I chose to go and approach this function from the right-hand side, and when I mean the right-hand side, if you look at your number line, and here's 6, I'm going to choose numbers that are positive on the positive side of 6, so I'm going to approach it from the right-hand side. If I'm approaching from the right-hand side, I'm using that second piece. I want to see what's happening to the values of the y's as x get closer and closer to 6. So I'm going to look at only at y2. So I'm going to set this up so I got the table set. I'm going to explore values very close to 6. And when I say close to, I'm going to go by 0.001. So I'm going to go 6/100ths of a way, and I'm going to change my ASC that I had in the previous problem to auto. And then I'm going to go look at my table of values. So I'm going to back away from a little bit. If I go to 6.1, I want to look at my y sub 2. That was that second piece. I was at 40.5. And then as I approach getting closer and closer to 6, what are these y values getting closer and closer to? What I can see is that those numbers are being driven towards 40 as well, so that equals 40. So what I want you to do to give me and provide me a little evidence of this is say, well, at 6.01, we got a value of 40.05. At 6.02, you got a value of 40.1. Show me that as you approach 6, these values are approaching 40. So here's the evidence I'm looking for. So that's part 2. Part 3 is I'm going to calculate the limit as x approaches 6 from the other side, the left-hand side, which I put the negative side, which means on the smaller side of f of x. If I'm on that side of it, then that's going to be using this piece. We are on the left-hand side of 6. So I want to look at what's happening to the outputs as x's approach 6 from the left side, which means I'm going to be looking at the y sub 1s. So my y sub 1s, as I approach, I'll just bring them back down here. If I go to 6.1 again, I can show you that it starts at 41.21 and it starts to get closer and closer to 40 as we get closer and closer to 6. So this limit of our function as we approach from the negative side is also approaching 40. And once again, the evidence that I'm asking you to show me here is by taking a few of the values that you have in your graphing calculator and show me that when you tested a few values here, so 6.01, you had a y value that was 40.12, 6.02, and you can, a couple is enough, we can show lots and lots of evidence by looking at that window. But as these numbers get closer to 6, these numbers are getting closer to 40. So in our continuity test, here's what we have proven. Number 1, we have proven that this function is defined at 6, which means there's not a hole here. It's defined. At 6, there's a 40. And then as we approach it from either side, as I approach it from the positive side or the negative side, it's going to approach 40. So I was going to use that number line there, but I think let's come back over here. So at 6, we'd have an output of, let's say this is 40. 6 would be 40. It's defined. As we approach 6 from the positive side, we're coming down towards 40. So we're approaching 40 from the top side coming down. And on the other one, we are approaching 40 from the top side. So that one was coming down here like this. So these two are both approaching the same value of 40 when it's defined at 40. So what we're doing is we're squeezing it in towards our point of contention. We're proving to you that it's defined at 6, and as we approach 6 from either side, it's approaching the same output, so therefore it must be continuous. That's the idea behind the continuity test. So what we say is, we summarize, so because f at 6 exists, and f, the limit of f at x, as x approaches 6 equals 40, it approaches 40, then our function is continuous at x equals 6. So continuity test, proving that it has to exist and that it approaches the same value from either side.